Okay, good morning, everybody. Hope you guys are doing well. Um, all right, so let's kind of go through and make some remarks here again. So, what I did is exactly what I did. I'd say exactly what I said I would do. Sorry. Let's go back to the browser here, or let's go to the browser. And okay, there we go. All right, so we're on the web page here. And what we're looking for is Math 262. And in Math 262, I want to remark again, you got your test 4, which is also your final exam study guide. And that's going to be due on, it's actually due, well, let's first of all take a look at it. Here it is. And it is a bit lengthy. So anyway, it's due, if we look at the schedule, it's actually due Tuesday before your final. All right, so at 6:99 a.m., your homework 4 is due. This test 4 is due at that particular time. And what we'll do after that point is have your final at 7 a.m. on Tuesday, June 2nd. So that's where everything is going to be due. And of course, pay attention to what we put in Canvas, because I will be posting things there as well, messages for you guys. And there it is. So anyway, we do have our test 4 on, it's supposed to be Monday, but it's going to be a take-home test, which is functioning also as your study guide for the final, and that's due right before the final exam on Tuesday, June 2nd. Okay, so I'm going to give you that day on Monday, June 1st, that Monday. I'm going to let you guys work on that test. So, I won't have any lecture that morning, and you guys will work on that test, and you guys will, at test 4, hopefully, give you a little extra time. Don't take your time, so there won't be any class on Monday, June 1st. You guys can be working on that test 4 study guide, and you will be preparing to turn all that stuff in Tuesday morning, June 2nd. At the deadline will be like 6:59 a.m. So that's what's happening. So I just want to review that for you guys, because it's the last day of the week. And there you go. Okay. So we talked about, here's our homework from Maclaurin series. We're going to do a couple of more examples and ideas that's in this section that actually you might see on that, take-home test 4. And so let's go through the book. And take a look at a couple of ideas. Of how we actually use some of these, power series expansions. So here's an idea. We're going to look at the limit here, looking at your book. Limit x goes to 0. 1 minus cosine x over 1 plus x minus e to the x. Now, this kind of question you've kind of had in the past. I guess you can say, it's indeterminate, right? So if you look at that limit, the numerator goes to 0, the denominator goes to 0, and you would use L'Hopital's rule probably. And in this case, like in some of the other limits, you might have to use L'Hopital's rule once, twice, 3 times, and so you can evaluate limits that way. We also can use a power series expansion. So for cosine and e to the x, that's what we're going to do. So we want to use an expansion for cosine. And for cosine, you're going to have to dig out your expansion. So, typically what I would do for people, and let me check the website here. So typically what I would do if this was an in-class setting in your browser, I think I do have a series summary sort of cheat sheet. Okay, so this is what I would give for like your final and test 4 in class is this kind of series cheat sheet. Now, you guys can use that. It's on my website. However, I'm trying to find the other notes here. Yeah, it may not be here. Let me see if it's on worksheet. It may not worksheets and videos. It might be in worksheets. All right, instantaneous. Maybe not, but anyway. Okay, so that gives me an idea of where we're at with this. I used to give, and I would have given in class a sheet here that does have all your power series expansions for the ones that we talked about. And on page 803, you'll see a bunch of them there. But in our case here, for some of these questions, and I'll put it in purple, we looked at the expansion for cosine. So you have the sum here, 0 to infinity for cosine, -1 to the n, x to the 2n, that's even powers, 2n factorial, and it's alternating. And remember, this is good for all real numbers. You also have the power series expansion for e to the x. And this expansion is x to the n over n factorial. It's also good for all real numbers. And since we're on the topic, remember you have all the other power series expansions. N is 0 to infinity, x to the n. This is only good for -1 to +1, open intervals. And I think we have sine. And remember the difference between cosine and sine. There's a difference. This is going to be still alternating, but you have the odd powers and denominator. And then that's also good for all real numbers. And you have inverse tangent. So on a final, I typically give people these additional power series as like kind of a cheat sheet. And this is just 2n plus 1 over really 2n plus 1. And this is good for the closed intervals here. We include 1 and -1. Okay, let's just double check we're okay with these. So this is the expansions that I typically give on an exam. And you might say, well, how do I use that here? Well, you're going to replace cosine here with the expansion. Now, notice what that expansion really is, though. The cosine expansion is if we let n be 0, we get here 1. Now when n is 1, it's minus, and that's x squared over 2. When n is 2, it's plus, and it's x to the 4th over, it's really 4 factorial. This was 2 factorial, which is 2, and so on. So I'm going to write this expansion down. And then e to the x, we go through the same sort of thing. 1. Now that's when n is 0. When n is 1, we get plus x. N is 2 plus x squared over 2 factorial. And this goes on forever. So you're going to write the power series expansion for each one. Now, by algebra, don't forget that really we have to distribute the negative sign. The same thing here, you distribute that negative sign. So you end up with the following limit. limit x goes to 0. 1 minus 1 plus, now it's going to alternate, x squared over 2 minus x cubed over 6 plus, that goes on forever. So that's your numerator. Your denominator is 1 plus x minus, and you distribute that term, minus 1, and they're all negative. Minus x squared over 2 minus x cubed over 6, and that goes on forever. Okay, let's do some arithmetic here. Notice that these terms here are going to be 0. 1 and minus 1 give you 0. X and minus x give you 0. So we now have the limit here, as x goes to 0, of really 1/2 x squared minus 1/6 x cubed plus, this goes forever, minus x squared over 2 minus x cubed over 6, and that goes on forever. And I'm going to write it, I'm going to be consistent with how I write this. So it's going to be negative 1/2 x squared minus 1/6 x cubed, and that goes on forever here. Now, the question becomes, how are you going to evaluate this limit? Because again, if you put 0 over 0 here, right? If you look at that limit as x goes to 0, you get 0 over 0, so you have a problem. And you're going to say, am I going to have to use L'Hopital's rule? Well, maybe. I mean, you can. Eventually, though, let me say something here. Here's kind of a thing that we've been saying, that you want to divide every term by the highest power of the variable in the denominator. Now, the highest power gets very large because you have x squared, x cubed, x to the 4th, and so on. But notice something here. If you have the same exact degree, right, you could divide by that x squared. It's not the highest power, but let's see what we get algebraically. We get 1/2 minus 1/6 x, and plus, that goes on forever. So because that's 1/2, every one of those terms for the variables are going to have an x to a power, and that's negative 1/2 minus 1/6 x minus forever. So now as that limit goes to 0, we get 1/2 over, if we can never write, 1/2 over minus 1/2, and now that limit is negative 1. So here's another way we can actually go about evaluating a limit, simply using a power series representation. And that's kind of a question I was looking at earlier in the book here. It looked pretty interesting to do. So we can give you one of those. Let's see what else is somewhat interesting. Kind of related to this. They can even give you something kind of simple in a way. What's the power series expansion? For maybe sine squared x, or let's not do that one first. How about this? Let's find a question where there's a nice product, maybe. Oh, what's the sine series expansion for maybe e to the x natural log 1 minus x. Now, remember, what they really mean is the Maclaurin series. So here's kind of something from our book as well. And to remark, we didn't know the power series expansion for e to the x. We do. And we didn't know the power series expansion for natural log of 1 minus x. And I believe that question we do know those expansions. So this one is listed above. And then remember, I think we did derive the natural log of 1 minus x. And that was in a prior problem. So natural log 1 minus x. Actually, let's get the Maclaurin series. I think that was something that was in our book in section 12.8. So I think we derived that one as well. And so maybe you want to put that one to the list. So we're going to take a look and we're going to find that. We sure have that. Remember, this was minus summation x to the n over n, where n is 1 to infinity. And I think this was good for the absolute value of x less than 1. So double check. I know that this was done already. It might have even been in our video. And the terms here, if you look at the terms, it's going to be minus x minus x squared over 2 minus x cubed over 3 minus x to the 4th over 4. And you're going to do that forever. So this is natural log of 1 minus x. So I'm going to see here, refer to notes, and maybe you add to the list. But you have the power series expansion for e to the x right up here. It's very similar, but you have factorials. So this expansion is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and that goes on forever. So let's write this down all together because it's going to be very helpful. I need e to the x, which is 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24, because that's a factorial, and then times minus x minus 1/2 x squared minus 1/3 x cubed, and then that goes on forever too. So what you guys have to do here is that you have a product. So the question becomes then, how do we actually write a product here? So we're going to have to multiply. So let's write that down. Now, typically what they tell us for these kind of questions is they just actually say, and I'll go back over here, they're going to say to determine the first 3 terms. So you want the first 3 terms here. And there's various ways of doing this. I would say to you, I mean, your book describes a way that you just kind of put it under each other. Here's what the book says. So you say, okay, you have 1 plus x plus 1/2 x squared plus 1/6 x cubed. And then you have this, minus x minus 1/2 x squared minus 1/3 x cubed, and that's minus forever. And you're going to multiply. And so just use your distributive property. And one thing you could do is just say, well, I'm going to distribute here. So I'm going to multiply this first term with all these others, right? And you end up getting negative x minus x squared minus x cubed to the second power minus x to the fourth over 6 to the power over 6. And that goes on forever. Now multiply the second term with everything in the same way. So you're going to get minus 1/2 x squared. So plug it in where under that term. Minus 1/2 x squared. And then this is minus 1/2 x cubed. And then you get a minus 1/2. Minus 1/4 x to the fourth. And that goes on forever. So, I'm just going to use the straightforward multiplication from algebra. I'm not going to do what the book wants to do. And then now notice what you get. When you add your columns here, it looks like, well, you're going to get a minus x cubed, and we can add these. There's 2 terms there. That'll be 3 terms? 4 terms? Let's double check. Looks like nothing canceled. So here's what we get. Minus x minus 3/2 x squared minus, we're now in the x cube. Is that just simply minus an x cube? And then this is going to be another term, but we don't have to get that term. They only have the first 3 terms. Let's make sure our arithmetic is okay. Okay, so let's double check here. Minus x squared minus x cubed over 2. Okay. And okay. Now, minus 1/2 x squared minus 1/2 x cubed minus 1/4 x minus 1/2 x squared minus 1/2 x cubed and then it looks like minus 1/4 x to the fourth. Anyway, you guys could double check this here. Yeah, I think we're good. Here's where I'm at. Minus 1/2 x squared, we're there. And then minus 1/2 x cubed, and there's a fourth there. Anyway, okay, it looks like we might be okay here for this. Yeah, something's bothering me about this one here. So, okay, if we say minus x, make sure we have the right power series. So let's double check here. Minus x times 1, minus x times, that's a minus x squared, and then a minus x cubed over 2, and a minus x to the fourth over 6. Okay. And then we got a minus 1/2. I see what's going on. We forgot to do this. Here's the issue. Okay. Right over here, ladies and gentlemen. That minus 1/3 x cubed gets multiplied, so we're going to have to do some more arithmetic. There's what the issue is. Minus 1/3 gets multiplied to every term as well. And so that minus 1/3 here, x cubed, is going to be there. Okay, so let's go back. We do have a minus 1/3 x cubed term. And then we're going to the fourth. So it doesn't look like we have to go to an additional power there. All right, well, let's see what we get. We'll go with what we get here. Minus x minus 3/2 x squared. And that looks like a minus 1/3 x cubed. And that'll be minus forever. Yeah. Anyway, and again, this is good for whatever these power series were good for. Remember that you want to find that intersection of the intervals. And so this is good for the absolute value of x less than 1. So here's another example of what you want to do to get a power series expansion for a product. And then similarly, they want a power series expansion for maybe something like this. Say, what about sine squared x? And you might think, oh, isn't that going to be sine x times sine x? And again, they want the power series expansion for the first 3 terms. So here's another way you can do this. What you may want to consider here is an identity. Because as you've seen from the last example, you're going to have to do some multiplication. But let's recall that sine squared x is 1/2. What was that angle? Do you guys remember? What was that identity? It's 1/2 1 minus cosine 2x, which is really 1/2 minus 1/2 cosine 2x. So here you want to use the power series expansion. And this time it's for cosine 2x. So if we go back and we say, well, cosine, how did that work? We'll go back to your cosine. And for cosine over here, it's the even powers. And don't forget factorial, and it's alternating. Okay, so even powers. So here we have the summation of -1 to the n triangle to the 2n over 2n factorial. Excuse me, 0 to infinity. But here you're going to use the 2x. Okay, so you might say I have to expand 0 to infinity, -1 to the n, 2x to the 2n over 2n factorial. A little bit of algebra here gives you 2 to the 2n, x to the 2n. And here's what we can look at, or here's what we can consider. The summation 0 to infinity, -1 to the n. 2 squared is 4. So it's really 4 to the n, x to the 2n now, over 2n factorial. Yeah, let's double check it's the right expansion. I believe so. Even powers 2n. Yeah. All right. So it looks like we're okay. So So if we look at the terms here, and the terms are going to give us, with n is 0, we get really 1. Now n is 1. That's minus 4 x squared over 2 factorial plus, now n is 2. 16 x to the 4th over 4 factorial minus n is 0, 1, 2, n is 3, 4 to the 3rd power here. 64 x to the 6 over 6 factorial, which is, well, it's 6 factorial. And that goes on forever. So if I try to simplify here, we know that the terms will look like this. This down here is going to be 2. 4 factorial is 24. And then you have here 6 factorial. And you say, well, what is 6 factorial? Well, let's think. 6, 5, 4, 3, 2, 1. 30 times 12 times 2, or 30 times 24. You could write it this way. Double check my arithmetic. 0, 12, that's 720. I think I'm good. Okay, let's erase this scratch work. So the terms look like 1 minus 2x squared. And then 16, 8 goes into 16 twice, so it's 2/3 x to the 4th minus, and then you got that 64 over 720 here. X to the 6, you can simplify that. 32 over 360, 16 over 180, 8 over 90. So it looks like it's 8 over 90. So double check. So what we're going to do is we're going to use this here in our expansion. Those are the terms. So you might say you have still the 1/2 minus. So we're going to have 1/2 minus 1/2 times 1 minus 2x squared plus 2/3 x to the 4th minus 8 over 90 x to the 6, and that's going to go on forever. So we get 1/2 minus 1/2 plus x squared minus 1/3 x to the 4th, and then it'll be plus, looks like it'll be 4 over 90 x to the 6, and it alternates. So double check to see if we're distributing okay, meaning right here. We distribute. Minus 1/2 plus minus plus, and it looks like here these terms are going to cancel. So, you know, the first 3 terms, if you looked at it that way, x squared minus 1/3 x to the 4th plus 4 over 90 x to the 6 minus, here's the first 3 terms, and you've expanded that as a power series, and that was good for whatever cosine's good for, which is all real numbers. So cosine's good for all real numbers, and so was this because it's cosine 2x, or really, sorry, sine. Well, it's really sine squared, but we're using the power expansion for cosine, so we go with what's cosine. Okay, so that's all real numbers. So here's the first 3 terms. And that's what happens when you actually could look at using the trig identity. Is that right, Kirby? 64 over 720. Is that 4 over 45? Okay, we'll go with that. We'll go with what you have here. So let's go back. 64 over 720. This is what Kirby's saying. We're going to go with what Kirby says, because you guys are more awake than I am. So 4 45, and that's x to the 6. Let's double check. So we had, it was 64 over 720. Don't have that. Okay, we're going to take your word for it, Kirby. 4 over 45. That's x to the 6. That'll be plus 2 over 45 now. I guess it's safe to change the color. Okay, we're going to go with the recommendation. So good for you guys. Okay. And then you might say they want the power series expansion for secant. You go, well, how do I handle that? Well, remember what secant really is. That's 1 over cosine. So we're going to use the power series expansion for cosine, but this time we're going to have to divide. And remember the power series expansion for cosine. And you go, well, is that going to be, see, I think cosine, is that even or is that odd? We have it right here. It's even for cosine. So alternates x to the even power over even factorial. Starts at 0 and 1. And the terms look like this. When it's 0, that's 1. When it's 1, that's minus x squared over 2 factorial plus, it'll be x to the 4th when it's 3, 6 factorial minus x to the 6th over, now it's 0, 1, 2, 3. All right, and it's 0, and it's 1, and it's 2. That's going to make this 4 factorial and 6 factorial. We should see that here because it's the same power. 2, 2, 4, 4, 6, and 6. And if we simplify that, that's 1 minus 1/2 x squared plus 1 over 24 x to the 4th minus 1 over 720 x to the 6th. And that goes forever. Now, don't forget, what we have to do here is we take 1, and then we have to divide by this whole thing. 1 minus 1/2 x squared plus 1 over 24 x to the 4th minus 1 over 720 x to the 6th, and then that goes on forever. So this is a division question. And we can write it as a division question. And this goes into 1. Okay. I wish I could move this all to the side. I get a little more space there. Well, we're going to have to divide here. And we need to use our division algorithm. You guys are going to see why I say I need more space. Now remember how you do this. You're going to take 1, you're going to divide it by 1. So the first step is 1 over 1, which is 1. There's the first step. And so you say, well, where do I put that 1? Well, typically you put that 1, you typically put it above the same term. So here's 1. Now, the second step in your division algorithm is to multiply. You take this 1 times this whole thing, okay? And so you say, well, what do I get when I multiply? That multiplication step, I'm going to put multiply here, but we put it down here. So you get 1 minus 1/2 x squared. Now you guys know why I need more space. 1 over 24 x to the 4th. Okay, step 3 is we subtract. So we're going to subtract, meaning we change the sign. So I'm going to change the color here. Subtract. And when you do that, you end up with, I'll put it here, 1/2 x squared minus 1 over 24 x to the 4th. And then it's going to be plus 1 over 720 x to the 6th. Okay, I know I couldn't write it down, but I'm going to do that. And that's your subtraction step. So let's double check. Multiply, subtract. Okay, and then you say, what do I do next? Well, you bring down the next term, but there's no term to bring down. So at this point, you're going to have to repeat your process. And you say, what's the process? Take the 1/2 x squared divided by 1. So you say 1/2 x squared divided by 1 is 1/2 x squared. You say, where do I put that? Well, you put it above the term, but it's not there. And then you multiply, step 2. So multiplication is going to be done with this 1/2 x squared to every term again. And then you end up with 1/2 x squared, and let's be careful, minus 1/4 x to the 4th plus 1 over 48 x to the 6th power, and that's multiplication. Third step is to subtract, which is changing every sign. And so here's what we're going to end up with. Let's be careful here. Right? We got I'm going to remind you guys here. Multiply this by 6, right? So you end up with 6 over 24 minus 1. So it looks like it's going to be 5 over 24 x to the 4th. And then you got this other term with an x to the 6th. So you get 170, you're going to get this arithmetic. 1 over 720 minus 1 over 48. Now, that's going to be to the x to the 6th power. So we're going to say plus 1 over 720 minus 1 over 48 x to the 6th power. And there's another term there. So we're just right here. This is why I needed more iPad space. Let's double check. Okay. All right. Now, it just turns out, I can multiply 15 and get 720. So here's what we end up with. 5 over 24, x to the 4th here. It's going to be minus 14 over 720, x to the 6th. Yes. And then you can simplify this. 5 over 24, x to the 4th minus 2 goes into 14 7 times, and that's 360, x to the 6th, and this is plus. Okay. Absolutely. All right. Just want to make sure there we go. There we go. Okay. Now you might say, well, what is all this? This is just the arithmetic that we get when we subtract. Okay. So if I can move all these terms up here, I would. Maybe I will. 5 over 24, x to the 4th minus 7 over 360, x to the 6th plus, and now you say, well, I bring down the next term, but there's nothing to bring down. So you repeat the process. And you say, what's the process? You're going to take this first term and you divide by 1. And you're going to get the same term. So this will be here plus 5 over 24 x to the 4th. And then this is going to go on forever. So here's the first 3 terms. When you divide it, here's what we can say. That the power series expansion for secant is what you guys see up here. One plus 1/2 x squared. And then the next term was plus 5 over 24 x to the 4th. So here's another way we can use that power series expansion. All right. Those are pretty good questions. And I'm just looking here. What's our time like? Okay, how about if we look at something like this? Maybe we could do another. We can integrate. We can, here's one. I'm not sure if I did this yesterday. I might have. You can integrate e to the minus x squared dx. I might have done that in the past. I'm going to say see notes. That looks familiar to me. Of course, you're going to use a power series expansion here. And you'll end up with n equals 0 to infinity, -1 to the n factorial, x to the 2n plus 1 over that 2n plus 1. So let me do this all together here. So see notes, essentially you're doing the power series expansion here. You're integrating this. You say this is 1, and that's a minus, so it would be a minus. What are you guys going to use? Right? That expansion, e to the triangle. 1 plus triangle squared over 2 factorial plus triangle cubed over 3 factorial. That goes forever. So this is going to be 1 minus x squared now. Plus, you say I'm going to square that, x to the 4th, and then that's over 2 factorial. Plus, it's really going to be a minus now. Looks like it's going to be x to the 6th. That's over 3 factorial. And that goes on forever. So this is why you say, okay, I'm going to end up with, and there's a constant here somewhere, but you're going to end up with this x minus, by properties of integrals, 1/3 x to the 3rd power plus 1 over 2 factorial times 5x to the 5th minus 1 over 3 factorial times 7 x to the 7th forever. And don't forget there's a constant here. And you get x is 1/3 x cubed plus 1 over 5, 2 factorial x to the 5th minus 1 over 7, 3 factorial x to the 7 plus forever. And I want to remind you here, I can sneak in here a 1 factorial, and I can sneak in here a 0 factorial and a 1. And you might say, why? Because this is how we have 1, 3, 5, 7. That's odd. That's the odd representation. And you say, okay, how do you represent that? You represent it this way. 2n plus 1. And then you already have the factorials. 3, 2, 1, 0 right here. And then again, these powers here. 1, 3, 5, 7. So this is how we have the odd powers. And then it alternates. So that's the answer. And I guess you have a constant c. So let's really be correct. And that's good for all real numbers because you're using the exponential function. And then, of course, if they asked you to approximate this integral, they said, okay, approximate e to the minus x squared dx from 0 to 1. Well, you're just going to use maybe the first three terms. You have x minus 1/3 x cubed plus 1 over 2 factorial 5 x to the 5th 0 to 1. So you plug in these values. You say 1 minus 1/3 1 cubed plus 1 over 2 factorial 1 to the 5th minus 0 minus 1/3 0 cubed plus 1 over 2 factorial times 5 0 to the 5th power. You end up with 1 minus 1/3 plus 1/2. Yeah. And so that's going to be 6 over 6 minus 2 over 6 plus 3 over 6. Let me double check. Which is 7 over 6. So this integral is approximately 7 over 6 numerically. Double check if my arithmetic's okay. Yeah, let's double check because I'm not even awake here. So I'm going to say times 2 times 2. This is times 3 times 3. Yeah, okay. It looks like it might be okay. 3. Yeah. Anyway, this is some of the work we can do with power series expansions. And then I'm going to want to remind people maybe, you know, the difference between Maclaurin series. We also have Taylor series. Right? So we have the summation now here. 0 to infinity. Fn a over n factorial x minus a to the n. Remember, Maclaurin is when a is 0. Taylor is when a is not 0. So they might say, what's the expansion? They want you to expand. We'll write it down. The Taylor expansion for sine at pi over 3. This is no longer at 0. So this is the a value, ladies and gentlemen. So it's going to be around this value here, or at this value, right? And we forgot to say here, let's write it down, that this is going to be for the absolute value, x minus a less than that r. So you want that Taylor series expansion for sine around pi over 3. So really, the focus will be on your constant. Here's what you really focus on. But because a is not 0, it's pi over 3, we have to take derivatives now of, here's the function sine. So, all right, we start with f of pi over 3 which is sine of pi over 3. And that's going to be square root of 3 over 2. We need f prime of pi over 3, and the derivative of sine is cosine. And so this is going to be 1/2. We need the second derivative. And say, okay, what's the derivative of cosine? It's minus sine, so that's minus sine of pi over 3, which is minus square root of 3 over 2. Third derivative at pi over 3. Okay, derivative of sine is cosine, and that's minus cosine at pi over 3, which is negative 1/2. And then you say, okay, what about the fourth derivative then? Well, derivative of cosine, what's the derivative of cosine? Minus sine, that's back to being sine pi over 3, square root of 3 over 2. So guess what? We have a repetition. This will repeat. This is the same as f. So here's our pattern. F of pi over 3. So this pattern will repeat. This sequence will repeat. You'll have square root of 3 over 2, 1/2, minus square root of 3 over 2, minus 1/2, and that repeats forever. So what that means here is we have to use this formula. So that's going to mean if we divide now by, we can say, we could do this, right? This is divided by change the color. 0 factorial, 1 factorial, divided by 0 factorial, 1 factorial, 2 factorial, 3 factorial. So let's see this Taylor series expansion. These are my coefficients here, all together now. I just looked at the whole thing together. Your coefficients. So you said, what were the coefficients? Remember, this is C0, C1, C2, C3, and then that pattern continues. So here's how we can describe this series here. It's sine x. Square root of 3 over 2 plus 1 over 2 factorial times that 1, x minus pi over 3, minus square root of 3 over 2 times 2 factorial, x minus pi over 3 squared. Let's double check. Yeah, plus, well, it's plus, minus, and then minus. So you get another minus sign here. We get 1 over 2 times 3 factorial, x minus pi over 3 to the third power, and then the process continues because these coefficients continue. So let's double check. Yes, 0 factorial is 1. We got that here. I put 1 factorial there. I could put a 0 factorial, but I don't have to. And then we got the 2 factorial constant, 3 factorial constant. Yeah, so it looks like we're okay with those constants here. And this is now what we call the Taylor series expansion for sine function about pi over 3. And okay, so let's go back. Let's try to make a nice square. Okay, here's your Taylor series expansion for sine. Because these terms are alternating, well, let me take that back. It's not alternating, if you guys know. It's, and there's going to be, wait a minute, something's bothering me. There's a 1/2. Square root of 3 over 2 Yeah, it should be a 2, I think. Yeah, this term is a 2 here. Okay, because they all end in 2. So yeah, we're good now. Just checking the terms. Square root of 3 over 2, 1/2, minus square root of 3 over 2, minus 1/2, and then we have the factorials. So here you can have maybe a 1 factorial. But Taylor series about pi over 3. And so all I'm doing is just using our Taylor series formula format and focusing on finding the constants. This is that Cn over here. And there you guys go. So let's double check to see the study guide, and hopefully it'll make some sense to us. Study guide, where are you? I go all the way down here. It looks like we covered some of the things that we needed to kind of talk about and cover. Oh, I did 41 for you. Oh, I did 40 and 41. Darn it. I didn't want to do that. Did I even do... oh, I did 36. Darn it. So it looks like I did 3 of those questions for you. Oh, sorry. I didn't mean to do that. Maybe 4. Anyway. Probably did a lot more than that. Not sure. Okay, ladies and gentlemen. So, yeah, this looks like we concluded for what's on our study guide. And again, I can lecture on Monday, but I don't think so. I think what I'll do is just let you guys have that time so that you guys can prepare for your final. Use that Monday morning time to do that. And again, if you have any questions or issues, you can always contact me. Office hours, email. Make sure, like I said, since we're at the very end here, you guys also know, if we look at the schedule, your final exam here is going to be on Tuesday, June 2nd, 7 a.m. to 9 a.m. Okay, so I'm going to have to make a somewhat shorter exam, much shorter than your test 4. And I guess if you guys like, we can start early at 6:30. So if you guys want, I'll give you an extra half hour for you. And let's go back to the iPad Pro. So if you guys want, you can start your final at 6:30. But it's really 7 a.m. to 9 a.m. And then, make sure that you guys can do things like upload. Okay? Make sure you guys can upload correctly. Because remember, you want to upload as a PDF. Upload as a PDF file. So make sure you guys have those kind of skills there. Okay? So on the Canvas assignments again, Kirby, can you be a little specific? Okay, yes. Oh, I think I understand your question, Kirby. Yeah. So, okay. So here's the deal. We got to extra hour. Okay. So if you guys want, look, listen, the problem with what's being done is on final exam week, the school created this list of when finals are. So if you're saying you want an extra hour, then the only way that can happen is if you actually start at 6 a.m. All right, you guys understand? Because there's final exams that might be after for you. So that's kind of, for some people, they're going, oh my God, I got to wake up early. Well, yeah, I guess. So that's if you want the hour. So should we start at 6 or should we start at 6:30? If you want to start at 6, click the like button. right? If you want to start at 6, click the like button. All right, I don't see any likes. All right, and that means 6:30. Okay. Well, I tried. Anyway, Kirby, I think I understand the meaning of your question. Yes, everything you guys turn in, you want to turn in on the assignment portion in Canvas. And so I will actually put that there. So you don't upload to the quiz portion ever. Never upload to the quiz portion. You always upload. Oh, it looks like we're getting likes. We always upload to the assignment portion, whether it's homework, test 4, or final. I will label that completed homework 4, completed test 4, completed final, and it'll be in the assignment portion. Now, the reason we have to do it this way is because in order to grade it in Canvas, like on an iPad, so you don't have to print things out and write things on. In order to do it, it has to be in the assignment portion. It's kind of crazy that Canvas didn't have that built in. That's insane. It's like, of course you grade quizzes like you grade assignments. Why don't you allow the grading to occur that way? In the same way, it doesn't. And that's a crazy thing about Canvas. So anyway, yes. So it's going to be uploaded to the assignment portion. Everything gets uploaded to the assignment portion, and I'll label it as such. So just make sure you guys are good with knowing how to PDF, scan with an app on your phone, PDF, not zip, not image, and upload, and we'll give you guys that extra time. Okay? So anyway, if you have any questions or issues, you can always come by office hours or email me. And I wish you guys all the best. I'm really sorry for how this semester turned out in the sense that, we transitioned online. I think we did the best we could under the situation. And I hope you guys, stay safe always. And I wish you the best. Anyway, take care. And I'm going to let you guys go because I have another class coming up shortly. And just looking for some stuff here. And anyway, yeah, take care. And I'll see you guys later.